Very good afternoon. Am I audible?
Yes, sir.
Yes,
Yes,
sir.
sir, you are audible.
Okay. Thank you. Okay, so we are going to start our last session for today's event. So this is a laboratory session, and uh, that session will be based on that demonstration oriented real-time integration and experimental demonstration of a DC microwave system. Okay, so that demonstration will be done to our lab. Okay, so over to you, Jayadev. We can run our system. Before that, he will give some of the basic idea on that, the real-time experiment. Okay, Jayadev?
Yes, sir. Thank you, sir.
Okay. Okay. Okay, you please share your screen.
Yes, yes. I think it is visual, right?
Yes, it is visible.
Yes, sir. Good
Sir,
afternoon,
visible but
everyone.
not clear.
Not clear.
Maybe I think network issue, but it's visible. Okay, I think some clarity issues are there.
One second.
Sir, screen is very blur.
Let me change my internet setting.
Hello.
Yes, now it's properly visible. Okay. You share your screen, yes.
Hello, am I audible, sir?
Yes, you're audible and your screen also being visible.
Yeah.
So make it full
Yes,
screen.
sir. Yes. Hello, good afternoon, everyone. My name is Jayadev, a research scholar in the NIT Rourkela. In this session, it's a laboratory session. In this session, we are going to demonstrate a 500-watt DC microgrid, which consists of PV, pico hydro generator as a sources, and battery for the DC link stabilization, and with a DC electronics load. Before going to the experimental setup, I like to introduce something, background of this setup. This is the content where the introduction, then block diagram of the DC microgrid, which we are going to present here, then experimental setup, then I'll conclude this session. Why we need the integration of multiple sources? Why it is necessary? It has some inbuilt advantages like resource diversification, like combining different renewable resources reduce the dependency on a single source. Like if you are installing a PV system in our home, then if some seasonal variability, it depends on season. If the from cloud come, then PV generation will be reduces for that. But our demand till now it at the peak value. So to meet that demand, we need another sources, or we will depend on grid for that time. If you use different sources like PV, wind, or pico hydro, or any other renewable sources, then the dependency on the grid will be very much reduced. At any condition, we will have a sufficient power for our load demand. Like grid stability, if anything happened to a particular source, still now we can able to supply the full load to our demand. Then reliability, if some variation in there, if solar, for example, in solar, some cloudy came, irradiation become reduces. For that, the power also reduce. In that case, we can rely on the pico hydro or a battery. At that time, other two sources will take care of the load. Then, like another is like an environmental benefit. This is the main prime point here. Um, our government and everyone also recently shifting from polluting biofuel to the renewable sources, so that the emission will be reduced and to make environmental out clean. For this system in real life, where this system will be implemented, like remote and isolated power system, where that grid connectivity will be very difficult, like hilly area or in a very remote area, or you can build a data center. Their DC supply is very much necessary, like independent military and aerospace system, and the individual electric vehicle charging system that you can build anywhere. Even if they don't have any grid also, we can build this type of system, or you can make a smart home and building. In this area, we can implement this system. Next, coming to this is our block diagram, which we are going to demonstrate here. We are using two sources. One is PV, another is pico hydro generator, and battery for the DC link or backup purpose only in this case.
Your
To
slides are not
integrate,
changing. Can you check it once?
to integrate all the sources, we need some DC-DC or interfacing converter. For PV, we are using SEPIC converter to integrate into the DC link, and for pico hydro, we are using diode bridge fed buck converter, which the pico hydro will generate the AC that will be rectified with the diode bridge rectifier. Then it will be stepped down to the required DC link voltage. And the battery we are using lead acid battery, which is for the backup purpose. For that, we need a DC-DC converter which can capable of bidirectional capability, which have bidirectional capability. In this case, you are using bidirectional buck boost converter. Whenever the power will be more or demand is less, and but our sources are generating more than the demand, at that time that extra power will be fed back to the battery for charging purpose. And whenever the demand is more than the our supply, that battery can support that extra demand. This is the overall system which we have built here. For PV system, we are using PV emulator as a PV system. Then the SEPIC converter, which is also built by us only.
Excuse me, sir.
Yes,
The
yes,
slide
sir.
is not changing.
Screen not changing.
Here we are seeing only your title page.
No, it's changing. It's changing from my end.
It is changing. It is changing. I guess.
Hmm.
It is changing, sir. It is changing.
I
Okay,
think
sir.
your network issue. Jayadev, please carry on. It's working.
Okay. This is the overall system we are using. For PV system, you are using a PV emulator of as a PV source. Then a SEPIC converter we are built by our own, and which is integrated to the DC link voltage. For Pico hydro generator set, we are using Pico hydro generator set for hydropower as a hydropower generator. Here, the induction motor used as a prime mover for the synchronous generator, and that power converted to the DC. Then again, step down through a buck converter, and then integrate into the DC link voltage. And here, the battery bank we are using battery bank for the required voltage level. In this case, the battery are 42 ampere hour at 12 volt. These are combined in series so that the current will remain in the limited in the range, and the voltage will be added off. And this battery bank integrated into the DC link through the bidirectional buck boost converter. And finally, you are feeding programmable DC load as only this time only you are using any only resistive load only. And coming to the system, the SEPIC converter, which we are going to see here, SEPIC converter, that we have built with the IGBT module, and we are using some semicron driver circuit to trigger this IGBT. It has inductance of value 6.08 millihenry. Both inductor have the around same millihenry. Those inductor also built by us only. That core we are using is EE8040. For the required current size, we have decided to take the current width as 12 SWG, and the capacitor which are used here are 4700 microfarad 450 volt and 2200 microfarad 450 volt. This inductor, this SEPIC converter can handle 1 kilowatt. According to our design, it is tested up to the 1 kilowatt at 15 kilohertz frequency. As this IGBT module can operate up to 20 kilohertz, but for the safe side, you are using 15 kilohertz only. Then the buck converter, we are used to integrate that Pico hydro generator. This buck converter we have designed up to 2.5 kilowatt at 15 kilohertz, which can sustain up to 10 ampere and 250 volt. And coming to buck boost converter, this is also 2.5 kilowatt converter we have designed, which can sustain up to 15 ampere and 250 volt. We have tested already, and switching frequency we have taken same also 15 kilohertz. This as the figure 7 shows the PV emulator which we are going to use as a PV source, And the lead acid battery for the storage element 42 ampere hour at 12 volt capacity we are using. And trigger to trigger all these switches, IGBT switches, we are going to use C2000 TMS 320F2379D launchpad. To generate, we integrated this launchpad with the MATLAB. From there, we are generating the pulses to trigger all the IGBT. Now we'll see the demonstration part, how we integrate all these sources and feed a 500 DC load.
It is visible, right?
Yeah.
Okay.
Visible.
Yeah.
It's visible.
This is the PV emulator, which will be used as a PV source. Then from this PV emulator, the SEPIC converter will connected, and from the SEPIC converter, we are connecting this load. This is the electronics load, DC electronics load. This DPDT and DP SD switch you are using as a DC link. For the DC link, we are considering this as a making as a DC link, and we are integrate. This switch will be integrate PV into the DC link, and this switch will integrate Pico Hydro into the DC link. And similarly for the battery system. Here, the battery lead acid battery we are using here. This lead acid battery output will be connected to the bidirectional buck boost converter. From this bidirectional buck boost converter, we are connected this to a DC link. Similarly, this is the buck converter. The direct bridge fed buck converter. The Pico Hydro output from the Pico Hydro generator, we are getting three-phase supply. This three-phase supply we are rectifying into DC, then again step down to the required value, and from the output of the buck converter, you are connecting this to the DC link voltage, and this DC link is connected through a switch crossover switch uh, to the DC electronics load. And the pico hydro generator, here the pico hydro generator is set up. We'll turn on this pico hydro generator and we'll maintain the DC link voltage here is 110 volt. And according to that, we will operate it 100. We'll see here the voltage, DC link voltage, load voltage in and current, then the power. First we'll go for 100, then 200 watt, then 300 up to 500 watt we can see here.
Your load, where is your load, resistive load?
This is a DC electronics load. This is resistive only.
Okay, okay. Electronic load, okay.
Electronics load.
Right.
Let me turn on the system. You can see the PV output coming from the emulator. It's set at 110 volt. Now we will turn on the battery system. Around 110 from the battery also. Now we'll set the pico hydro. Set the pico hydro. Let me change. we will integrate this PV. Two point five there it's showing. It's operating at 300 watt. 300 watt. All our system are connected. This is from Pico Hydro. It is integrated to the DC link. This is for battery and this is for PV. All three systems are integrated together with the load. If I change here the current, I'll change the current here to 3 amps.
Your bus is 48 volt or 110 volt?
This is 110 volt. We are maintaining
110,
this link
okay.
voltage as 110.
Fine, because in theory we heard 48, so I'm just trying to
Around
compare.
3 ampere, 110 volt. If you
Great.
see the current,
What is that instrument name, sir? The electronic load, ISS something is there. That instrument name.
it's from 1.5 ampere from the Pico Hydro. Then the battery, it's drawing around 0.4. The PV. It's drawing 0.9 amps. Change this, make it to uh, 4.5 amps. Now it's operating at 400 watt.
Right. GIE.
It's operating at 400 watt. Around this is how it's operating. All the system are connected. There the Pico Hydro generator are running. From there, Pico Hydro, they are supplying all this.
So from 48 volt DC battery, you are, you are upgrading to 100 or 110 volt, right? From the DC.
1 second, sir. That because the machine you are not able to clearly understand. 1 second.
DC motor generator. Your video is very clear.
So was the final setup. Now we are coming to the PPT. Then I will take any query will there. Then I will answer it.
So this was our setup for 500-watt DC microgrid, where we are successfully integrate pico hydro, PV, and battery to the electronics load. So these are references, and thank you. Anybody have any doubt?
If you are having any query, please let us know.
Hello, yes.
Yeah.
From where you are giving the pulses to using C2000 microcontroller?
In MATLAB, we are combining the building that code, and we dump into C2000 launchpad. From there, we are giving the supply pulses.
Okay.
There is a special session for this how to build code into the C2000, how to generate proper pulses at all the frequency, and how to set the frequency also and duty ratio to generate required pulses.
So you are using TMS 320, right?
Yes.
So from MATLAB code, you are dumping in there. Okay.
Yes, sir.
Right. Okay. Then only that 4 batteries are there, except batteries.
Yes,
so 48 that the DC you are making it 100 110, or you are keeping it 50 only. 48 volt
110,
DC.
sir.
100K, right? So 100 watt. Yeah. That's good. Yeah. Your setup is very good.
Excuse
you,
me.
Yes, sir.
What is the specification of PV emulator and what could be its cost?
Cost. It is specifications is 2 kilowatt. This PV emulator is 2 kilowatt.
2
It is
kilowatt.
100 volt. Maximum we can supply give from 100 volt, and current is 20 ampere only. So this was the
voltage.
maximum voltage 100 watt.
Achha.
This system was around 3 to 4 years back. We purchased. That time it was cost around I think not sure, but it's around 2 lakhs, 2 to 3 lakhs.
Yeah.
If it is 2.5 lakh.
Yes, see, particularly in R&D, the cost we cannot, will be definitely will be high, and depending on the environment and the people involved. R&D
Yes.
cost we cannot match with the market cost, right? So
Yes.
once it is in the market, it will be very less. So R&D cost will be tricky. You cannot say, because that is the expectation of the researcher and the resources available. So the cost,
Actually,
when people are asking, R&D
sir,
cost naturally we can. Yes, sir.
Yes, you are right, sir. But he is telling about the cost of the PV emulator. So if we connect the system with our rooftop PV, definitely the cost will be cutting down.
Yeah,
Okay, so 2.5 lakh, that cost we are talking about, that is PV emulator cost. Okay, sir. And
Yes, sir. Yes.
we are they are designing the converters and all those things in our lab itself. So individual converter may cost around, I think, in current scenario, it may be 10 to 12,000 for individual converter. And if we directly connect the natural resources, renewable resources, instead of that, we are sometimes using emulators. Okay, so that's why if we see the overall setup cost may be high, but if real time when you are going to implement, for the actual renewables. So overall converter cost is not more than, I think, maximum 50,000. Okay, overall setup maximum.
Right, yeah. That's commercial market cost.
Yes, yes, maximum.
And DC bus voltage we are maintaining at 110 volt, right?
Yes, ma'am.
Okay.
So is it going to increase market cost if it is not, if I'm planning at 2 kilowatt?
Yeah, if actually if you increase the power level, na, so because of power level, the components, all the component will be higher size, higher component will be required. The inductor size also bigger, and the main cost component is the heat sink. It's
Yeah.
very costly. So with power, the cost will be increased.
The similar thing, we are actually planning to do 2 kilowatt because a motorcycle can be in Indian environment, a scooter like
Yes.
Honda can be charged. And the 2 kilowatt will helpful for the domestic also. So if the model, if you can make around 2 kilowatt, because in
Yes.
simulation, taking 500 watts instead of taking 500 watts, if you do it at 2 kilowatt, probably, and then immediately it can be deployed to the commercial requirements. Is it so?
Yes, sir.
Probably we'll be in touch with you because we did most of the part. We are doing it for 5 kilowatt. Certain things were missing. After seeing this, I thought I think we'll be in touch with you and then go further.
Yes, sir. It's
Sure,
a
sure,
good.
sir.
Yes. You can definitely. If we are always trying to do the collaboration because we are also scaling up the system. Another demonstration will be there. I think couple of days. That also been I think integrated with the wind. I think so. So we are also going for some scaling up of our system. Okay, so definitely we can collaborate. No problem.
Thank you very much.
Okay, sir. Thank you. Is there any other queries from that esteemed participant in? Okay, so I think there is no other queries. So thank you, Jayadev, as well as
Thank you,
that
sir.
yes for the demonstrations. Okay, so thank you all the esteemed participants because today this is our the last session. Okay, so tomorrow morning again we will start from 9 a.m. sharp. Okay, so in the meantime some recorded video we are going to share in that chat box, and the meeting link whatever we have shared that will be the same. Okay, there is no changes in our meeting link. Up to end of program, it will be same. Okay, so thank you.